So what is quantum physics? It's the science of the tiny, of the matter and energy that makes up our universe. So there's physics of the big, and there's physics of the tiny. So it's quantum physics. Okay, so what is this quantum revolution, quantum computing and all this stuff? Well, it turns out we've already had a quantum revolution, right? We had quantum 1.0. That was where we made lasers and the microchip and solar cells and all these devices that run off of quantum physics, but you're not actually using individual particles like atoms or ions or interesting devices like superconducting circuits, which require the fridges that Chris makes. And so this is the 2.0 revolution, where now instead of using a silicon chip that has a transistor that stores the information as 0 or 1, we now use like an atom or an ion or a photon, particle of light, and it can stay in a weird combination state, superposition state. That's something that's very, very quantum. We don't have that. It's like the Erwin Schrödinger cat, right? If anyone's heard of the dead or alive cat, we don't have zombie cats just walking around. It's either dead or alive in our world. Well, in the quantum world, it can be in this weird superposition. And then we can harness these quantum bits, these qubits, to do really, really, really vital, important calculations. So for example, like AI is already being used for optimization. There's machine learning. That is not quantum. AI is not quantum. That's the other thing I want to say really quickly. That's classical computers all working together that have learned together of how to teach each other. That's classical computing. And the way to scale it up is by making more and more computers and more data centers and more power plants. That is not quantum. With quantum computers, every qubit, you get exponentially more power. And it's just a different computational system, so you just can solve problems that are not solvable with our classical computers. And then the final thing is the quantum threat. So in about 5 to 15 years, we might have the fault-tolerant quantum computer that we've heard about just a little bit so far. That's the holy grail. We don't have that yet. We're in the era of noisy qubits. So we have usable systems that are being used right now, and I can tell you case studies of real businesses implementing logistics, things like this with quantum. But we don't have a fault-tolerant quantum computer. And why does that matter? Because it can run Shor's algorithm. And if you know anything about encryption, that can break RSA encryption, which is a very common public key encryption. So that means a lot of the stuff that we use online for banking and secure communications and public key could be vulnerable. And we've known about this for a while. We've known about this since the 80s. And so there are quantum solutions like quantum, post-quantum cryptography, and I could go on and on and on.